So here we go with the big idea to move into Calculus 2, the idea of a limit. Limits are related to infinity. And so we're just going to look at a bunch of examples about how that works. So super simple one here. 1/3 is a beautiful fraction, right? I can cut a pizza into thirds, for example. Pretty good at that. However, people prefer decimals, but 1/3 as a decimal is kind of a pain in the butt. It's 0.333333, and those threes keep on going forever. Every time we add another 3 decimal there, we get closer to 1/3. Now, each of these threes here actually has some significance, right? This one is 3/10, that one is 3/100. So another way to look at this is 3/10 plus 3/100 plus 3,000, and so on, right? Is 0.33333 the same number as 1/3? The answer is no. This number here is a little bit smaller than 1/3. If I really want to get 1/3 as a decimal, I have to let those threes go on forever, but that's a problem because I cannot go on forever. Right? I can't keep adding forever, neither can my calculator, neither can my computer. So what we say here is that these two are equal in the limit as these threes go on forever, right? So the limit of this process of adding 3/10 and 3/100 and so on, right? So eventually I'm going to have something like 3/10 to some power, right? First power, second power, third power, fourth power. The limit of this process, right? Limit is kind of like a boundary, right? I can't go beyond a certain limit like a fence. So the limit of this process of adding 3 over a power of 10 over and over and over again is 1/3, right? If I can keep doing that forever, I will get 1/3, but I can't go on forever. And so the limit is kind of a little mathematical cheating word to say, well, you know, you tell me how close you want me to get to 1/3, I'll tell you how far out to go in this list here, is the kind of idea. It's kind of a dare. Okay. You say, I need to be within a billionth of 1/3, and I say, great, go out to this spot right there, and you'll be close enough. How does this relate to the idea of instantaneous rate of change? Instantaneous rate of change is the idea of slope at a point on a curve. So I am going to pick a curve. Let's do a pretty basic one. Doesn't get more basic than y equals x squared, curving, that is. And quick sketch of that. And I'm going to pick the point 1, 1. I want to know what is the slope of this curve at 1, 1. So let's go out. Let's say that's 1 right there, and let's let this be 1 right there. 1, 2, 3, 4, 2 would be about there. See, this would be 2, 3, 4. So I know this graph has a point at 0, 0, and 1, 1, and 2, 4, and at 1/2, 0.25, about right there. And so this curves, sometimes I'm not so good with this magic pen. So that's a rough sketch of my y equals x squared. And I want to know the slope again at this point right here. And I can see that this curve is shallow. It's not very steep at the bottom. So if I was walking up this hill, no problem here. But then all of a sudden, right about here, I'm like, man, this is getting steep. And up here, like I'm a mountain climber, right? So here's my estimate of that slope right there at that point. and I want to try and calculate what it is. Now, problem with slope is I need 2 points. Okay, so, well, that's clearly one of my points. And then my other point could be something like, the 1/2, 2.5, or I could get closer. So I'm just going to pick some point over here. And I'm not going to actually name a number there. I'm just going to call it x. And if I plug in x, then the y value there is going to be x squared. So my 2 points are 1, 1, and x squared. And we know that to find the slope, we have to do our whole f of x2 minus f of x1 over x2 minus x1. So I'm going to call this point 1 here. I'm going to call that point 2 right there. So then I get x squared minus 1 over x minus 1. And I can pick different numbers for x to plug in there to see what's happening and find out where that slope is heading. So this right there is a formula for the slope of 2 points on the curve y equals x squared. And I'm leaving the point 1, 1 fixed, but I'm letting this point right here, I can move it toward that point if I want by picking x values closer and closer to 1 on either side. And I'm going to do that on a spreadsheet. So let's get a spreadsheet out. My Google Drive has lovely spreadsheets to work with. Spreadsheet is a beautiful calculator, right? Every cell is its own calculator. Let's get a new sheet. And I'll share this with y'all if you want. This could be useful for some homework problems. And let's zoom in a touch on that. Hopefully that's good. So I need to keep track of my x. Ooh, yeah, got it. Thank you. Bye, Google. I need to keep track of my x value. Might as well keep track of the y value too, which is x squared. And then I want to keep track of the slope. And we know we're fixing the point 1, 1. Actually, I'm going to calculate it. The y value is always equal to the x value raised to the second power. And then otherwise, I'm picking other x values that are close to 1. So in my picture, I had something below. Like maybe I'm starting off at, say, 0.8, and then I'm going to go to 0.9, and then maybe 0.99, and 0.999, right? So I'm getting closer to 1. So calculating those y values equals the x value squared. And then Google says, hey, you want to keep doing that? Yeah, I do actually. Okay, now the slope's a bit more complicated. Slope requires 2 points where I'm always going to use that point right there. So let's highlight that one. So I can't do a slope on that line, but I can do a slope on this line. So I always want to use that point there, and then this one, and then that one, and that one, and so on. So equals, my numerator, parentheses, is going to be this y value minus that y value. And I always want to pick that yellow y value. And I'm going to be moving this formula down, row 2, then row 3, row 4, row 5, and so on. Or sorry, row 3, 4, 5, and 6, and so on. And so to tell it to always pick row 2 for the second one, I just sneak a $sign in front of the 2 saying, hey, don't touch the 2 when I fill that formula. Close the numerator, divide, denominator is this x value minus that x value. And again, I always want to pick the x value from row 2. So I just sneak a little $sign in there. So this formula right here will find the slope for any other point down here and always use the point 1, 1. So there's my first slope, and Google says, yeah, I'll fill that down for you. All right. So I see a pattern going on here. I'm going to guess that, again, as that point gets closer to 1, 1, the other point, the slope seems to be getting close to 2. Now, we're only looking on the left side. We should look on the other side, too. So, for example, 1.1, or actually, let's go 1.2, kind of match what I did above. So here I'm 2/10 below, now I'm 2/10 above. And then 1.1, 1.01, 1.001. All right, so there's a set of points here. same distance away, x values are the same distance away as these points on the left. And really all I need to do is fill down these two formulas now that I made that. And yeah, it looks like a little higher than 2, but as this x value gets closer to 1, the slope seems to be getting closer to 2. So this is the idea of a limit. And if someone says, well, that's not exactly 2, I need you to get closer to 2, I can say, okay, well, just pick some x values that are closer to 1. So then I could go 1.0001 and 1.00001 and so on. And as I fill these down, I'm just going to keep getting closer and closer to 2. And somebody says, well, I need you to be a little closer. I can say, fine, I'll just pick an x value closer to 1, and I'll get you a slope that's closer to 2. But it looks like 2 to me. Will it always be a number we recognize? The answer is no, actually it won't. Okay, so this is slope on a curve. And I'm going to share this in the Zoom chat and in the video description. Let's get the share going here. You guys, you might find this useful in your homework. I'll show an example of why it's useful in the homework in a minute. Let's make sure anyone can view it. There we go. So if you want to use the spreadsheet, go ahead. And when you open that link up, by the way, those of you looking at this now or in the future, if you're signed into Google, then you'll be able to make a copy of it. At the moment here, I am not signed into Google. Oh, we have, yeah, I see people jumping in there. Anonymous Dingo and Anonymous Squirrel, cool. So let's say if I were signed in, oh shit, I didn't want to do that actually. Then what I would do is make a copy of it for myself to use. Otherwise, I only gave you view privileges of this. I don't want you messing with my sheet, so you'd have to make a copy of it if you want to actually do something with it. And again, another example, I'll show how to use this for one of the homework problems. Okay, back over to this problem here. So we played around with letting this x value here approach 1. And as we let approach 1, it didn't matter whether we approached from the left side or the right side, the slope seemed to approach 2. Okay. Now, I put a question mark by seemed because I'm not 100% sure, but I have some pretty convincing evidence there, right? Let's get that spreadsheet back in view here. 2.1, 2.01, 2.001, 2.0001, and so on. That's looking like it's heading toward 2. And same thing over here, 1.99, 1.999, right? As x creeps closer to 1, the slope seems to be creeping closer to 2, right? I'm fairly convinced about that. Would I testify in a court of law on that? Yeah, this is clear and convincing evidence beyond a reasonable doubt, in my opinion. All right. Now, that right there is what we call inductive reasoning. I have this sequence of events that seems to be leading me toward a place, but sometimes we need a little bit more proof than that. Now, this idea of x approaching and the slope approaching, that's the idea of a limit. And sometimes, like in math, we don't like to write that many words. So I'm just going to write this in a slightly different way. As x approaches 1, so that arrow means approaches there, my slope, x squared minus 1 over x minus 1 was the slope formula I was using. That seemed to be approaching 2. Now, with a limit, we approach but don't touch. Why not? Right, we want to get close on each side, but not actually touch it. Touching it is kind of cheating. So I'm going to cheat here for a second. Cheat by plugging in 1. Sometimes you get lucky. So if I plug in 1 to my slope formula, I get 1 squared minus 1 over 1 minus 1, which is 0 divided by 0, which does not exist. Darn. But it looks like 0 over 0 in this case is 2. Interesting. Now, you can get lucky with some algebra if you happen to make an observation. And we're going to do a lot of lucky algebra over the next several weeks. X squared minus 1 factors. It's equal to x minus 1 times x plus 1, which is rather fortuitous because I have an x minus 1 in the denominator. And I am familiar with the fact that a number divided by itself is 1. So that means x squared minus 1 over x minus 1 is equal to x plus 1 on one condition. That condition is if x is not 1, right? Because if I try to plug in 1 to the original, I get 0 over 0. Whereas here, if I cheat and plug in x equals 1, I get 1 plus 1 is 2. And I have now further evidence that the slope of y equals x squared at the point 1, 1 is 2. So let's check that on a calculator to make sure I didn't do some insanity math there. That's not true. I'm going to whip out my Desmos calculator. And I have f of x equals x squared. Beautiful. And then I have the point. I'm going to use my function notation for point 1 comma f of 1. I highly recommend you get used to using function notation in the Desmos calculator. So there's my point right there. And then I'm going to graph the line that has that slope. And so remember the point slope form of a line. If you don't, I'll write it down for you. So let's check. Let's write this in red, maybe. Check by graphing. And we're going to use the point slope form of a line, point slope line, which is y minus y1 equals m times parentheses x minus x1. And my x1, y1 is the point 1, 1, right? That's the point I'm looking for the slope at. And I believe the slope is 2. So we're going to plug that into this formula in Desmos and see if that line looks like it mimics the slope of the curve. All right, y minus 1 equals 2 times parentheses x minus 1. And yeah, look at that. That is what we call a tangent line. It's a line that touches a curve at a point but doesn't actually cross through the curve. And we could zoom in on that sucker and see. All right, we could expand that a little more, but that looks pretty good. I look like I have a tangent line there. Yeah, so this line right here does have the same slope as the curve at that point. And that slope is 2 over 1, or 2. So we are going to use the idea of limits to help us with the idea of instantaneous rate of change. And so limits and instantaneous rate of change, that's our mission all quarter. We're just going to work on that problem. It turns out we need all quarter to work on it. It's a tough problem.